Okay, this is part two of the videos. Yesterday we did all this, or in the last video, we did this. Here's the backside to it. We're going to go ahead and factor difference of squares. So take a minute, go ahead and jot all this down. I'm going to assume that was already done, and we're going to jump in, okay? So here's what we're going to do. We're going to kind of lead into this. It says expand the following problems and look for patterns. All right. So I'm going to jet through these. Take a look at those problems. I want you to try to see as many patterns as you can for all three of these problems. Let me go ahead and just start expanding this. So I'm going to multiply this out. At x times x, that's an x squared. X times negative 2 is a negative 2x. 2 times x is a positive 2x. 2 times negative 2 is a negative 4. Notice that here in the middle, these are like terms, and so I can go ahead and combine them. When I combine them, they actually cancel out, so what I'm left with is x squared minus 4. That takes care of the first one. Pretty nifty that those canceled out. Let's look at the next one. I'm going to do the same thing, going to go a little bit faster this time since hopefully you understand what's going on. It's going to be x times x, which is x squared, x times 4, which is 4x, negative 4 times x, which is a negative 4x, negative 4 times 4, that's a negative 16, excuse me. Combine like terms. Oh, look at that, they canceled. I get x squared minus 16 as my answer. Looking for the last one. I got a 3x times a 3x, that's going to be a 9x squared. A 3x times a negative 4, that's going to be a negative 12x. 4 times 3x, that's a positive 12x. 4 times negative 4, that's a negative 16. I combine like terms in the middle. I end up with a 9x squared minus a 16. So take a minute, just kind of look at the process and try to see some of the things that you notice that's the same for all three of these problems. I'm going to go ahead and tell you 3 or 4 main things that students were saying in class today. The number one thing that always got brought up was like, oh, the middle term's always canceled, and so you're only left with 2 terms instead of 3, and that's absolutely true. Then once we started digging a little deeper, the other thing people started noticing, like, oh, this is one of a perfect square because it's x times x, and this is a perfect square because it's 2 times 2. Same thing with this one. This is a perfect square because it's x times x. This is a perfect square as well because it's 4 times 4. This is a perfect square as well because it's 3x times 3x. And this is a perfect square as well because it's a 4 times 4. So yes, every single time we did these problems, we ended up with perfect squares as our remaining result. The second to last thing students noticed was like, oh, on all my answers, there was a negative in the middle. All of these statements were perfect. And finally, some of us got it, some of us didn't. We kept multiplying by the same thing twice. The only difference is one had a positive, the other had a negative. One had a positive, the other had a negative. Here's the same thing twice, but one had a positive, the other had a negative. So we're actually going to use the fact that we have this pattern to go in the opposite direction. That is to say, I'm going to give you the answer here, and we're going to use the fact that this kind of patterns out to go backwards and end up with the factored form, which is looking like this. So when I have a minus b times a plus b, what would happen? Well, these guys would go a times a, and I would get an a squared. These guys would go b times b, and I would get a b squared. The stuff in the middle would end up canceling, but I would end up with a negative symbol in between. And if I have a minus b times a plus b, well, then that should be the same thing as a plus b times a minus b. So this is actually going to give me the exact same answer as well. This is still going to be a squared minus b squared. And again, our goal today is for you to realize, like, hey, there's a pattern here. If we call this a difference of squares, if you see something that's a perfect square and a perfect square and a subtraction in between, then I can actually factor it really fast by just saying, all right, well, what's the square root of this? What's the square root of that? I'll put one here. I'll put the other one there. Make one a positive, make one a negative. Like, it becomes really fast to factor these if you can understand the pattern. So let's go ahead and go over the steps. I put this as step 0 just because we should always be factoring out the GCF. Like, I don't even need to tell you anymore that you should be factoring out the GCF. That's just something that should be becoming automatic at this point. Okay, so step 0, factor out the GCF. You don't need me to tell you that anymore. Factor out the GCF, okay? Once you are factoring out the GCF, if you only have two terms, like usually when we factor something, it looks like this: 3x squared plus 2x minus plus 9, right? And I see 1, 2, 3 different terms. But sometimes you'll end up with something like this. If you only have two terms, it might be a difference of squares. It might be. It's not always, but it could be, okay? Here's how we're going to check. You're going to check if both are perfect squares, the first thing and the second thing. And you also need to have a subtraction symbol in the middle. If all those terms are satisfied, you have a perfect square on the first one, you got a perfect square on the second one, and there's a subtraction in the middle, then you're going to take the square root of each term, and you're going to write it as a sum and a difference of your roots. Again, always sounds like gobbledygook. Let's show you how that works, okay? So let's go. Step 0. Does this have a GCF? I see that it has two terms. Does it have a GCF? The answer is no. Okay, step 0 is done. Now I'm going to check. All right, well, there's two terms here, and you can factor it making an x. We're not going to do that. We're going to use a shortcut. We're going to see, are both terms perfect squares? Well, let's see. This is a perfect square because it's x times x. This is a perfect square because it's 5 times 5. So yes, this is a perfect square. Yes, this is a perfect square. And oh, look at that. There's a subtraction in the middle. Guys, this is a difference of squares. Since it's a difference of squares, then I know I can factor this really, really fast. All I have to do is I need to take the square root of this. How did I get that x squared? Well, that's an x times x. So I'm going to write this as, all right, that's an x times an x. How did I get the 25? Well, that must have been a 5 times 5. So this is going to be a 5 times a 5. And because it's a difference of squares, then one of these needs to be positive, the other one needs to be negative, and we are absolutely done. This x squared minus 25 factors to this. Now, I don't need you to do this, but I'm going to do it anyways, just because I want to show you that this does in fact work using an x if you really wanted to, okay? So remember, what do we put on the top? We go a times c, right? Remember that this is your a, this is a 1. This is your c, that's a 25, negative 25. So 1 times negative 25 is a negative 25. What's your b value? Your b value is 0 because you don't have a middle term. So in the middle, we're going to put it as 0. I need two numbers that multiply to negative 25 and add up to 0. Well, that's going to be positive 5 and negative 5. Because when I multiply them, I get negative 25. And when I add them, I get 0. And because my a value is 1, then I don't need to use the bottoms up method here. Like, I'm good to go. That means my first answer is going to be x plus 5. And my second answer is going to be x minus 5. Again, I get the exact same answer. The only difference is I don't need to do an x anymore. I can literally jump straight to my answer if I know the trick, if I can spot that it's a difference of squares. Okay, let's move on to the next one. I got 16x squared minus 9. Same concept. I look for a GCF. I don't see a GCF. Okay. I see that it's two terms. Hopefully this is a difference of squares. Let's see. Is this a perfect square? Yeah, this is going to be 4x times 4x. That's how I get 16x squared. And this is going to be 3 times 3. And I do have a subtraction in the middle. So this is a difference of squares. So that means I can pretty much factor my answer. I just got to put my parentheses down. To get the 16x squared, I know it's a 4x times a 4x. And to get the 9, I know that's going to be a 3 times a 3. To get the difference of squares, I make the first one positive, the second one negative, and I am done. I have factored this by using the difference of squares. Let's take a look at the next one. First step, 0 step is there a GCF? The answer is yes, there is a GCF. The biggest number that divides 81 and 9 is 9. So I'm going to factor out the 9 first. So this becomes 9 parentheses. 9 times what gives me that 81a squared? That's going to be a 9a squared. 9 times what is going to give me that negative 9b squared? Well, that's going to be a negative b squared. Now that I have factored out the GCF, now I realize that I only have two terms in here. And if it's two terms, hopefully it's a difference of squares if there's a subtraction in the middle, and sure enough it is. This is a 3a times a 3a. That's a b times a b. So I'm going to go ahead and write this as a 3a times a 3a. That's how I get the 9a squared. And then a b times a b. That's how I get the b squared. I need to make the first one a positive, the second one a negative. You put this in formative, it's going to mark it wrong because you forgot to bring down your GCF. So you need to bring down that 9 in front. And now we are correct. Look how faster this is. I don't need to make an x. You could make the x if you wanted to. It would still work. You know what? We'll show you that real quick. I'm going to start straight from here. Remember, it's 9a times -1. That's a -9. And then 0 on the bottom. I need two numbers that multiply to -9, add up to 0. That's going to be a -3 and a +3. However, because this has a 9 in the front, you need to do what we did last time and make it over 9. Make it over 9. This becomes -1/3. This becomes 1/3. There is your 3a minus b. There is your 3a plus b. And you got to be careful because you're using a's and b's here. The bottom ones are your a's, the top ones are your b's. Okay, so that's even a better reason why you don't want to do it with the x method. You might forget your variables. Okay. All right, last one, same thing. Is there a GCF? The answer is yes. Be careful. This GCF is going to be a 3 and a y. They both have a factor of 3. They both have a factor of y in it. So I can't take out two y's because this one doesn't have two y's to take away. So I write this as 3y times parentheses. How do I get this back? This is going to be a 25y squared. How do I get this back? This is going to be a -4. Now, I hope and I pray that this is a difference of squares. It is. This is a 5y times a 5y, and that's a 2 times a 2. So I go ahead and drop my parentheses. This is going to be a 5y times a 5y, and then a 2 times a 2. One of them has to be positive. The other one has to be negative. You drop down your 3y. I had a really, really good question in class today. It only happened once, but man, oh man, was it a good question. The question was, Mr. Lechuga, what if instead of this, which is obviously a difference of squares, I had this? What do I do then? And the answer is, let's see. What happens is this a difference of squares? Well, this is a perfect square because it's x times x. This is a perfect square because it's 3 times 3. But this is not a difference. This is a sum. So this is not a difference of squares, which means our shortcut should not work for this. But just to prove it to you, let's go ahead and do it the long way by making an x and see, does it in fact work? Well, let's see. I'm going to go a times c, which in this case is going to be 1 times 9. That's going to be a 9. And I don't have a middle term, so I put a 0 down here. I need two numbers that multiply to 9 but add up to 0. And you go, oh, well, of course, 3 and 3's got to work. Except when I add 3 and 3, that's going to be 6. So obviously, you have to change one of them so that it's negative. So now this works. -3 plus 3 is 0. But -3 times 3 is not 9. So that doesn't work. What if you put the negative on the other side? Well, you got the exact same answer, right? Like that really doesn't change anything. And if you put negatives on both, well, that doesn't work either because now you got a -6. And I think we said like, oh, if you put a 3 and a 3 like this, then that doesn't work either. So we tried all the combinations, guys. This doesn't work. So what do? Well, in the formative, you're going to write not factorable if you get something that looks like that. Okay. We tried all these different methods. None of them worked. All right, go ahead and take a minute. Try this out on your own. I'm going to assume you already did that, and I'm going to jam through these just because I don't want the video to be long. So, difference of squares, yep. X times x, 6 times 6. That's going to be an x times an x with a 6 times 6. Make one positive, make one negative. That one was super easy. I'm going to skip this one for now because students were having trouble on that one today. Let's go over here. This one's a little bit easier. Let's go 50x squared y minus 18y. What is the GCF? If you said that the GCF was 2, you are super close. What else can I factor out? They both have a y, therefore I can factor out the y as well. Now that I have that, then I can go ahead and do this. 2y times what? That's going to be a 25x squared will give me the 50x squared y. And then 2y times what is going to give me -18y. That's going to be a -9. Is this first one a perfect square? Yep, it's a 5x times a 5x. And this one looks like a 3 times a 3. So I write this as 5x times a 5x and a 3 times a 3. Make one positive, make one negative. Bring down your GCF. And now for the one that was giving people problems. Is there a GCF? The answer is no. Are these perfect squares? The answer is yes. This is a 7x squared times a 7x squared. That's how you're going to get that x to the fourth. And this is an 11y squared times an 11y squared. That's how you're going to get that 121y to the fourth. So that was messing up students all day. Let's go ahead and write that. That's a 7x squared, times a 7x squared. That'll give you the 49x to the fourth. And then I said the 11y squared and 11y squared. Make one positive, make one negative, and you are good to go. That's it for the notes for today. As always, if you have questions, please feel free to ask.